Hello everyone, I am Krishna Gupta. I am Assistant Professor in Electronics and Communication Engineering Department in AKGEC Engineering College, Ghaziabad. In this lecture, I am going to discuss the Cascade amplifier and about the negative feedback structure. So the contents are Cascade amplifier. Then we'll discuss about the general feedback structure, like what are the different types of feedback, and after that we'll discuss about the properties of negative feedback. In the properties, I will discuss about the advantages and limitation of negative feedback. So starting with the Cascade amplifier. So firstly we need to understand that what is Cascade amplifier, what is the need of Cascade amplifier. So before that we should be able to understand the common source amplifier, that is in short that is called a CS amplifier, and common gate amplifier. Individually we need to understand that, like in MOSFET there are three configurations: common source, common gate and common drain, and in BJT there are three configurations: common emitter, common base and common collector. So we had studied that in the common source amplifier there is a Miller effect. There is a Miller effect because a capacitance, internal capacitance, that is called CGD, gate to drain capacitance, that is connected between two high gain node. Because of that the input capacitance C in is increased, and because of the increase in input capacitance C in, the upper 3 dB frequency is reduced, and if upper 3 dB frequency is reduced, then bandwidth of the amplifier will also decrease. That is called Miller effect. So in common source amplifier there is Miller effect, and due to this Miller effect the bandwidth of the amplifier is reduced. That's why we don't use common source amplifier for high frequency applications, because of this Miller effect. Bandwidth is very limited for common source amplifier. That is the limitation of common source amplifier. But there are some advantages of common source amplifier. That the first advantage is its input resistance is high. The input resistance of common source amplifier is high. The reason is, in common source amplifier we apply the input signal at the gate terminal, right? So we know that this gate current Ig, that is equal to 0. That's why the input resistance of common source amplifier is very high, and for voltage amplifier it is very much desirable that the input resistance should be high. That is the advantage. And another advantage is transconductance is higher for common source amplifier. That these are the advantages of common source, but the issue with the common source is there is Miller effect, and due to that Miller effect bandwidth is reduced. As far as common gate configuration is concerned, common gate amplifier is concerned, in common gate amplifier we apply the input signal at the source terminal. We apply the input signal at the source terminal and we take the output from the drain terminal. So the input resistance of common gate is low in comparison with common source amplifier, because you can see that in common source amplifier we are applying the input signal at the gate terminal. In common gate amplifier we are applying the input signal at the source terminal. So the input resistance of common source is much higher than the input resistance of common gate configuration. So this is the limitation of common gate. That limitation is its input resistance is low. Fine. But the advantage of common gate amplifier is that it can be used for high frequency application. It has better high frequency response. Reason is there is no Miller effect in common gate. So we had seen that there are various advantages and limitations of common source and common gate amplifier both. For example, for common source amplifier the advantage is input resistance is high and transconductance is higher. But the problem with the common source amplifier is its bandwidth is reduced because of Miller effect. And the advantage of common gate amplifier is that there is no Miller effect, so it can be used for high frequency application. It has better high frequency response. But the issue with the common gate is the input resistance is low. So if we see individually the common source and common gate, then we are seeing that there are various limitations of common source and common gate. So the cascade amplifier, it combines the advantages of common source and common gate amplifier both in a single configuration, in a single circuit. It combines the advantages of common source and common gate both. So in cascade amplifier, we use two configuration at a time. The first one is common source and the second one is common gate. So you can just check that the advantage of cascade amplifier is that its input resistance is high, transconductance is higher, as well as it can be used for high frequency application. It has better high frequency response, right? So the basic cascade amplifier, it consists of two transistors, Q1 and Q2. The lower transistor is Q1 and the upper transistor is Q2. We can see that this Q1 transistor, it is in common source configuration. It is in common source configuration. Since Q1 is in common source, it means that we are applying the input signal at the gate terminal of the Q1, and since it's a common source, so we will take the output from the drain terminal from here. Now the output of common source amplifier is the input of the common gate amplifier. This Q2 is basically common gate. In common gate, we apply the input signal at the source terminal and we get the output from the drain terminal. You can see that the output of common source, we are taking it from drain terminal and we are giving the output of common source from drain terminal to the source terminal of Q2, and at the source of the Q2 we are applying the input signal. So the upper transistor Q2 is in common gate, but the input signal is obviously it will be applied at the common source configuration. The reason is, if we are applying the input signal at the gate terminal of Q1 transistor, then input resistance will be high. Since the gate current is 0, practically it is very less, right? So here we are using two transistors and we are using two different configurations, common source followed by common gate, and we are applying this VG2, this is the DC bias voltage, at the gate terminal of Q2, just to ensure that Q1 and Q2 transistors should be in saturation region, because MOSFET works as an amplifier in saturation, and this current source I, it provides the necessary bias current. So this is the cascade amplifier using MOSFET. When we design cascade amplifier using BJT, in that the lower transistor will be common emitter and the upper one will be common base. So that cascade amplifier is the combination of common emitter and common base, but in case of MOSFET, it is the combination of common source and common gate. So I have already discussed the basic idea behind the cascade amplifier, that is to combine the high input resistance and large transconductance achieved in CS configuration. These are two advantages: high input resistance and large transconductance of CS configuration with the current buffering property and the superior high frequency response of CG, that is common gate circuit, right? The common gate is having current buffering property because the current gain of common gate configuration is unity. So cascade amplifier, it can be designed to obtain wider bandwidth, and obviously with equal DC gain we will get sufficient DC gain as compared to the CS amplifier, because the issue with the CS amplifier is that because of the Miller effect, the high frequency response is very poor for the common source amplifier, and this drawback of common source amplifier, it can be removed with the help of cascade amplifier. And how we are removing it? Just we are combining common source configuration with common gate configuration. So these are just the basics of cascade amplifier. Now coming to the feedback. Basically you people had studied the amplifier earlier, and this amplifier, it can be used in two configuration. One is open loop configuration and another one is closed loop configuration. So if we are not applying any feedback, feedback means output is connected to the input. So we will say that this amplifier is in open loop configuration. Let's say we are applying the V in voltage at the input of the amplifier, we are getting the output voltage V naught. Let's say the gain of the amplifier is A, so obviously this A will be output voltage upon input voltage. This A is called voltage gain. But see, this amplifier, it does not have any feedback, right? Now the next question arises that why we need to connect the feedback and what are the different types of feedback, what is the relevance of the feedback. Now see, if we connect output to the input and if output is subtracted from the input, that is called negative feedback. If it is added to the input, that is positive feedback. So basically the feedback is of two types. The first one is negative feedback and the second one is positive feedback. Negative feedback and positive feedback. In negative feedback, output will get subtracted from the input, and in the positive feedback, output will be added to the input. Basically, negative feedback, it is used in amplifiers. The reason is that negative feedback provides stability. It ensures that the operating point, it is in the middle of the active region for the BJT amplifiers and in the middle of the saturation for the MOSFET amplifier. Since BJT works as an amplifier in active region, MOSFET works as an amplifier in saturation. So that operating point, DC bias point, it should be at the correct location. Otherwise, we will get distortion in the output signal. For that, we do the biasing, right? In the biasing, there is a one method that you had studied. In that method, we connect a resistor at the emitter terminal of the BJT, and in the MOSFET amplifiers, we connect that resistor at the source terminal of the MOSFET. And this resistance, let's say this resistance is RE, it provides negative feedback. Basically, it stabilizes the DC operating point. So negative feedback is very much important in amplifiers because this negative feedback, it stabilizes the amplifier, and that is very important, because if the amplifier is not stable, how can we use that amplifier? So we need to stabilize our amplifier. For that, we require negative feedback. As far as positive feedback is concerned, positive feedback, it is used in oscillators. It is used in oscillators. Oscillator is an electronic device which is used to generate a signal of a particular frequency. Like you have seen oscillators in the laboratory also, like function generator, which can generate sine wave, square wave, triangular wave, etc. Right. So positive feedback, it is used in oscillators. So here in this lecture, I am focusing on negative feedback. Fine. So firstly, we need to understand that why we are applying negative feedback in the amplifier. The reason is negative feedback, it stabilizes the amplifier. This is one of the main reason, one of the advantage of negative feedback. But there are various other advantages also that we need to understand. So coming to the properties of negative feedback, or we can see that these are the advantages of negative feedback. Basically, when we apply negative feedback in the amplifier, it desensitize the gain. What does it mean? It means that it make the value of the gain less sensitive to the variations in the value of circuit components such as might be caused by the changes in the temperature. Reason is that if there is a change in temperature, because of that the circuit component values may change, right? But if the circuit component values are getting changed due to the changes in temperature, the gain should not change. The gain should be independent of the change in the value of the circuit component when there is a change in temperature. So by applying negative feedback, the gain, it becomes less sensitive to the variations in the value of circuit component. That is one advantage. Another advantage is that negative feedback, it reduces the non-linear distortion. That is very much required, because when we design amplifier, we want linear amplification, we don't want any distortion. So by using negative feedback, the distortion is reduced, the non-linearity is reduced. Another advantage of negative feedback is it reduces the effect of noise. So whenever we are designing any electronic circuit, there will be noise, because at room temperature the electrons move randomly. Because of movement of those electrons, a voltage is generated that is called noise voltage, and we need to stop that noise to go from input to output. For that we use differential amplifier, that is a different topic, but by applying negative feedback we can reduce the effect of noise also. Another advantage of negative feedback is that it controls the input and output resistance of the amplifier. That is another good thing. For example, if we are considering voltage amplifier, so for ideal voltage amplifier, the input resistance should be infinite and output resistance should be 0. So we want the input resistance should be high and output resistance should be low for voltage amplifier. So if negative feedback, it increases the input resistance and decreases the output resistance of voltage amplifier, then it's a good to apply negative feedback in the voltage amplifier. Similarly, there are other amplifiers also, like current amplifiers, transconductance amplifiers, trans resistance amplifier, and by applying negative feedback in these amplifiers, we can control the input and output resistance. Another advantage of negative feedback is that it extends the bandwidth of the amplifier. It can increase the bandwidth of the amplifier. That is another good thing of the negative feedback. And apart from five these properties, there is one thing which I have already mentioned, that is negative feedback. It improves the stability, it stabilizes the amplifier. Now coming to the structure of the negative feedback, that is a general feedback structure. So you can see that this is the basic amplifier, and the gain of the amplifier is A, and this A is basically gain without feedback, and the input signal is coming from the source. This source may be a sensor, right? And the input of this amplifier is Xi and the output of this amplifier is X0. This X is an electrical quantity, it may be voltage or it may be current. Now you can see that this output X0, it is going to the input of the feedback network, and the gain of the feedback network is beta. This beta is called feedback factor, and the output of the feedback network, it is Xf. Input of the feedback network is output of amplifier A, that is X0. So you can see that the feedback factor beta, it will be Xf upon X0, and amplifier gain A will be X0 upon Xi. Since the output of amplifier is X0 and the input is Xi. Now since this is negative feedback structure, so this Xf is getting subtracted from the input signal Xs, and we are getting Xi, and this Xi, you can see that this Xi will be equal to Xs minus Xf. So in fact there are three equations. One is A is equal to X0 upon Xi, another one is beta is equal to Xf upon X0, and the third one is Xi is equal to Xs minus Xf. So this is the closed loop system, this is the negative feedback structure. If we want to design positive feedback structure, then what will be the changes? There will be only one change. That change is this negative will be replaced with positive in the positive feedback structure. So if we are not applying any feedback, it means that there will be no feedback network, and that system is called amplifier without feedback. But we are applying the feedback, and we are applying the negative feedback in the amplifier, since it stabilizes the amplifier. So obviously this feedback network will be here. So with the help of these three equations which I have discussed, that is X0 equal to A into Xi, Xf is equal to beta into X0, Xi is equal to Xs minus Xf. After mathematical simplification, we can calculate the gain with feedback, that is called AF. This AF is also called closed loop gain, that is equal to X0 upon Xs, because the output is X0, input is basically that is coming from the source. So the gain with feedback, the closed loop gain, it will be x naught upon xs. So with the help of these three equations and after mathematical simplification, you can simply calculate x naught upon xs, and after the calculation we will get AF is equal to A upon 1 plus A beta. Now this AF is gain with feedback, A is gain without feedback. Gain without feedback means open loop gain. And what is beta? Beta is feedback factor. What is A beta? A beta is called loop gain. A beta is called loop gain, and the amount of negative feedback is called 1 plus A beta. Is 1 plus A beta. It is referred as amount of negative feedback. I repeat, beta is feedback network, and this feedback network, it is made up of passive elements like R, L, C, and the amplifier is made up of active element. Obviously we use resistor and capacitor along with the transistor, that is the active element, but the active element it is mandatory in the design of amplifier. Without active element we cannot design amplifier, but in the feedback network we use passive elements. Fine. So this equation AF is equal to A upon 1 plus A beta, it is the gain of the closed loop system, gain of the negative feedback system. Now I have already discussed about it, like A beta is the loop gain and the factor 1 plus A beta is called amount of feedback, amount of negative feedback. Now see, we have got this equation AF is equal to A upon 1 plus A beta, and we know that this loop gain A beta is very greater than 1. If loop gain A beta is very greater than 1, then this AF will be reduced to A upon A beta, because 1 will be ignored, 1 is very less than A beta, A cancel out, so AF will be approximately 1 by beta. So AF will be approximately 1 by beta. So see how we are getting this 1 by beta, because the loop gain is very high. If we are considering that assumption into our calculation, then we will get AF is equal to 1 by beta. So what does it mean? What does this equation signify? AF is equal to 1 by beta. It means that the gain of the closed loop system, it depends upon the feedback network. That is a good thing, because the reason is the feedback network consists of passive components that I have already mentioned, passive elements, passive components, that is resistor, capacitor and inductor, which usually can be chosen to be as accurate as one wishes. So the negative feedback results in the accurate, predictable and stable gain, because since AF closed loop gain is depending upon beta only, if we are considering loop gain is very high, so this negative feedback, it results in accurate, predictable and stable gain. So in other words, we can say that the overall gain will have very little dependence on the gain of the amplifier, basic amplifier A. That is very much clear, because initially we got the equation AF is equal to A upon 1 plus A beta, and we are considering A beta is very greater than 1, then we are getting AF is equal to 1 by beta. So AF is having very less dependency upon the gain of the basic amplifier A, and it is very much desirable, because this gain A is a function of many manufacturing and application parameters, and some of which might have wide tolerances. So we need to understand this point. This gain of the basic amplifier, that gain is A, it is the function of many manufacturing and application parameters. It depends upon many parameters, and those parameters, it may have wide tolerances. It means that wide tolerances means if there is a small change in those parameter values, then there will be a large change in the amplifier gain A, and that is not desirable, because we want stable gain. We want stable gain. Fine. So overall, we are seeing that by using negative feedback, the gain of the negative feedback system, it becomes less dependent upon the gain of the basic amplifier, and it comes as a desirable property. Now I am just going to discuss the derivation of few of the properties, like we have seen that this negative feedback, the gain desensitivity, it arises by using negative feedback. The bandwidth is extended and the noise is reduced, interference is reduced with the help of negative feedback. Here we are going to understand how, right? So to understand the gain desensitivity, again we are applying the same equation which we have derived, that is AF is equal to A upon 1 plus A beta. Now we need to find out the relation between DAF upon AF and DA by A. We need to find out the relation between these two, DAF by AF and DA by A. For that, what we do, we just differentiate DAF we just differentiate AF with respect to A. Now you know the formula of differentiation, just apply that formula, and after applying the formula, just divide AF to the both sides of the equation, and from there you can find out the relation between DAF upon AF and DA by A. And after simple mathematics, you will get DAF upon AF is equal to 1 upon 1 plus A beta into DA by A. So there is some meaning of this equation, this equation tells that the percentage change in AF is smaller than the percentage change in A. It is very much clear from this equation, because the change in A, that is DA by A, change in AF is DAF by AF, and you can see that the change in AF, it is lesser, it is smaller than the change in A. By which factor? By the factor 1 plus A beta, because this 1 plus A beta is in denominator. That is why this 1 plus A beta, it is also called desensitivity factor. So it is a very good thing, because the change in closed loop gain, it is very much smaller. It means that the closed loop gain is less sensitive to the variations in the circuit parameters. That is called gain desensitivity. It's a good thing, right? Because if the gain is depending upon the circuit parameters, so it means that if there is a change in temperature, then there may be a change in circuit parameter, and because of that the gain may vary. And remember that we want stable gain. Now the next one is bandwidth extension. Like I have mentioned that negative feedback, it increases the bandwidth of the amplifier. This is just the statement. Here we are going to derive it. Here we are going to understand that how negative feedback is increasing the bandwidth of the amplifier. For that, again we are using the basic closed loop gain equation, that is A upon 1 plus A beta. Here we have mentioned AFS, that is AF is the function of S equal to j omega. Since we are using the word bandwidth, and bandwidth is the range of frequency, we are using the word frequency here. So we are just writing A as a function of S, AF is a function of S. This is the basic equation which we have already derived for negative feedback system. And already you have derived for common source amplifier the gain of the common source amplifier, that is AM upon 1 plus S by omega H, where AM is the midband gain and omega H is the upper 3 dB frequency. So this upper equation, let's say this is equation number 1, this is equation number 2. This equation number 1 you had already derived in the high frequency response of common source amplifier. From there we are taking it directly, because we had already derived this equation number 1, and equation number 2 we have got in this lecture. We have derived this AF is equal to A upon 1 plus A beta. Now just put the value of AS, that is value of AS from equation number 2 into equation number, just put the value of AS from equation number 1 into equation number 2, and after simple terms arrangement, you will get AFS is equal to AM upon 1 plus AM beta upon 1 plus S by omega H 1 plus AM beta. So you can say that this is equation number 3, and just compare equation 2 and 3. Just compare equation 2 and 3. So coming to the numerator part, in equation number 2, in the numerator there is AS, in the equation number 3, in the numerator there is AM upon 1 plus AM beta. It means that the gain, the midband gain, it is getting reduced by the factor 1 plus AM beta. The midband gain is reduced by the factor 1 plus AM beta. And if we compare the denominator of equation 2 and 3, from here you can see that from just compare equation number 3 and 1. Don't compare 2 and 3, just there is a small change. Just compare equation number 1 and 3. If you are comparing equation number 1 and 3, then you can see that in the numerator of equation number 1 there is AM, and equation number 3 there is AM upon 1 plus AM beta, and equation number 1 it represents the gain without feedback. Equation number 3 it is the gain with negative feedback. So you can see that the midband gain AM it is reduced by the factor 1 plus AM beta, and the upper 3 dB frequency omega h it is increased by the factor 1 plus AM beta, right. So here what we are doing, we have got equation number 1 from the earlier derivation. That derivation was a high frequency response of common source amplifier, and equation number 2 we have derived it for negative feedback system, and we have put the value of equation number 1 into equation number 2, and after that we are getting equation number 3, and we are just comparing equation number 1 and 3, and from that comparison you can see that the midband gain is reduced by the factor 1 plus AM beta, and the upper 3 dB frequency is increasing with the factor 1 plus AM beta. Similarly, we can do it for the lower 3 dB frequency also, and you will get that the lower 3 dB frequency with feedback, omega LF is lower 3 dB frequency with feedback, it is omega L upon 1 plus AM beta. It means that the upper 3 dB frequency is increasing and the lower 3 dB frequency is decreasing by the application of negative feedback, and the bandwidth of the amplifier is omega h minus omega L, or we can write it fh minus fl. So with the help of negative feedback, with the application of negative feedback, fh is increased by the factor 1 plus AM beta and fl is reduced with the factor 1 plus AM beta. So overall effect is the bandwidth is increased. One more thing, the amplifier bandwidth, you have seen that the amplifier bandwidth is increased by the same factor by which its midband gain is decreased. Agree? Because the midband gain AM is decreasing by the factor 1 plus AM beta and the bandwidth is increasing by the factor 1 plus AM beta. So maintaining the gain bandwidth product a constant value. Of course, ultimately we will get the same gain bandwidth product because gain is decreasing and bandwidth is increasing, and this is the only limitation of negative feedback, and that limitation is negative feedback, it reduces the gain of the amplifier. We have seen that the gain of the negative feedback system AF, that is A upon 1 plus A beta. When we had not applied negative feedback, then the gain was A, and when we are applying the negative feedback, then that gain A is reduced by the factor 1 plus A beta. So this is the drawback of negative feedback, because by applying the negative feedback the gain is reduced. But why we are using negative feedback? Because there are many advantages of negative feedback, like it stabilizes the amplifier, it increases the bandwidth, it reduces the interference and noise, it can control the input and output impedance. There are various advantages of negative feedback, and it is having only one drawback, one limitation, that is gain is reduced. Gain is reduced. Although there is a solution for that. If the gain is reduced, so in order to improve the gain, in order to increase the gain, we can go for multi-stage amplifiers also. That is a different topic. So from this graph you can see that earlier the gain was this one, and when we are applying the negative feedback, then the gain is reduced, but you can see that the bandwidth is increased. So overall the gain bandwidth product will be constant. Now coming to the next one, next advantage of negative feedback, that is interference reduction. By applying negative feedback, we can reduce the interference, we can reduce the noise. To understand it, let's say the gain of the amplifier is A1, and in this amplifier A1 we are not applying any negative feedback. We have not applied any negative feedback, and the input signal is Vs, and let's say the noise added to the input of the amplifier is Vn. So signal to interference ratio, it will be Vs by Vn, and this Vs by Vn, it is for the amplifier without feedback. So ultimately what we are going to understand, if we can increase the value of S by I, signal to interference ratio, it means that the effect of interference will be reduced. So what we do, we just calculate S by I, signal to interference ratio, for the amplifier without feedback and for the amplifier with feedback, and from there we will see that for amplifier with feedback the S by I ratio is enhanced. So for the amplifier without feedback the S by I is Vs by Vn. Now when we are applying the feedback and the feedback factor is beta, then now we are going to calculate the value of S by I for this diagram. Now there is one thing which is important to mention here. To reduce the effect of interference and noise along with this amplifier A1, we need a pre-amplifier whose gain is A2, that is connected before this A1. That is another thing, because it means that to reduce the effect of interference we require two things. Firstly, we will apply negative feedback, and the secondly, we are in fact using the pre-amplifier whose gain is A2, and this A2 amplifier, it should be free from noise and interference, of course, right? And again the input signal is Vs and the noise is Vn. Now again we need to calculate the value of V0 here. To calculate the value of V0, we will apply superposition theorem. So as per superposition theorem, at a time only one voltage source will be there and others will be removed, and similarly case 1, case 2, we can get the V0. So let's say case 1, consider the case 1. In case 1, suppose that if we are removing this Vn and we are just connecting Vs here, so what will be the gain of this, what will be the output voltage of this circuit? It will be A1, A2, since this Vn is removed means it will be short circuited, then A1, A2 are in cascade, so A1, A2 upon 1 plus A1, A2 beta, fine. Similarly in the second case, Vn will be there and Vs, we will remove Vs. So in that case the gain, the output voltage, it will be A1 upon 1 plus A1, A2 beta, and as per superposition theorem we will add both the voltages, and after adding, the first term is this one is the second term. From here we can calculate S by I, just calculate the first term upon second term, this is the first term and this one is the second term. First term upon second term, when you put it, then you will get S by I is equal to Vs by Vn into A2. So just compare, when we are not applying any feedback, then S by I ratio is Vs by Vn, right? And when we are applying negative feedback, then S by I is Vs by Vn into A2. It means that with the application of negative feedback, the S by I is increased by the factor A2, where A2 is the gain of the pre-amplifier. That's why we require this pre-amplifier A2. Noted? So here we have understood that how negative feedback is reducing the effect of interference. For that we have calculated the value of S by I. So in this class I have discussed cascade amplifier, and after that I have discussed negative feedback structure. What are the advantages of negative feedback? What are the properties of negative feedback? There are various advantages, we have seen that, but only limitation is that with the application of negative feedback the gain is reduced. And after that we had understood that how gain desensitivity is achieved in negative feedback system, how bandwidth is increased with the help of negative feedback, and how interference is reduced with the help of negative feedback. This is the reference. Thank you.